Good afternoon, good morning, good evening, everyone, depending on where you're at. Welcome to the March 2021 NHWC webinar. My name is Brad Hallwagon. I'm the Vice President of NHWC. I'm facilitating this webinar today. Thank you all for your patience in the transition from registration on our website and Teams Live and all that over to this GoToWebinar platform. We recently just upgraded our GoToWebinar account so we could do these webinars, and we think it's going to really work out for us. Just note though that all lines are muted right now. If you have questions during the presentation, there's a question box that you should be able to type them into. What I'm going to do is I'm going to hold all questions until both presenters are done, and then we'll address those questions. And what I'm going to try to do is make it so y'all can unmute, and if you have some questions that are follow-up questions towards the end, I'll let y'all unmute your lines. But if that starts to get out of hand, if there's a lot of background noise, I may have to really quick remute those lines. So I guess we'll just dive right into today's presentation on collecting rainfall data. We have two great presenters, Jason Elliott from the National Weather Service and David Haynes from DDI. I'll let them do their own introductions today. And so with that, I'm going to kick things over to Jason and let him begin his presentation. All right, Jason, you should be the presenter.
All right, thank you. Hello, everybody. Looks like you can see my screen, so I think we're in good shape there. I'm Jason Elliott. I'm the Service Coordination Hydrologist at the Northeast River Forecast Center in Norton, Massachusetts. And the first question that might pop up is, why are you here to talk about this today? In my past life, 3 weeks ago, I was the service hydrologist at the Baltimore, Washington Forecast Office, worked closely with David and other folks. I consider DC to be kind of the king of flood warning systems. I can't think off the top of my head of any place else in the country that has more individual ones. There are probably bigger ones out there, but the DC area has like a billion different ones that are all doing their own thing in some ways, and then are all coming together in other ways. So in my past life, one of my jobs was to bring as much of that data as I could get my hands on into our operations and put it to good use and hopefully add value to it as well. So what I'm here today to kind of speak about is the role that we play in the National Weather Service in general in flood warning systems as a end user customer and as a partner to the operators of those systems, why they're important to us, how we can work together, and what we do with the rainfall data that comes out of these networks, which is essentially, and I'll put the bottom line up front here and say that essentially what we're doing with the data is the same thing we do with any other good high quality data that we bring into the system. It's treated the same way. So that's kind of the gist of what I'm going to cover, but let's get into the details. And then when I'm finished, David will pick up and talk about sort of the meat and potatoes of rainfall collection and flood warning systems and all that fun stuff. So ultimately, as I said a second ago, the Weather Service is a customer of a flood warning system. We're relying on the data for a number of purposes, but the reason we're most involved and we ultimately require access to the data is that our agency coordinates the hydrologic radio frequencies that a lot of the flood warning systems use to transmit their data out. So if you have a flood warning system already or you're thinking about starting one, it really pays to get to know your local National Weather Service point of contact. The best contact at your local office is the service hydrologist or the hydro program manager, because not every office has a service hydrologist. Now, with that said, I looked, there used to be a website that listed all the service hydrologists in the country. That website didn't get updated for a long time, and now I can't even find it. And So therefore, there is a map that shows every warning coordination meteorologist in the country. So if you don't know your local hydrology contact at the National Weather Service, reach out to the warning coordination meteorologist. They'll put you in touch with the person that you need to talk to. And there's a website there on the screen, weather.gov/stormready/contact, that takes you directly to that map and will get you the name of at least somebody in the right office. Plus, the map is broken out by county. So if you don't know which office covers you, you can go to the state, go to the county level, and see which office you actually need to make contact with. Now, with that background out of the way, part of the agreement to use Weather Service coordinated hydrologic frequencies is that we get access to the data. And the best way to share data with the Weather Service is to send it through the MEDAS system. That's the Meteorological Assimilation Data Ingest System. It's also because we love acronyms. But that doesn't mean that sending the data through MEDAS is the only way for it to get out. Even though the MEDAS system has become sort of a standard method after a couple different ways that data got through, we've sort of gotten to this one place and have been fairly stable, and now are able to expand it out to more and more systems. If you can't use that method, or you don't want to use that method, your local Weather Service office should be happy to work with you to get the data in whatever format possible. What I'm showing on the screen is the SHEF, Standard Hydrological Exchange format, that we ultimately in the Weather Service would like to receive data in so that we can process it into our hydrologic databases. And most of our networks are able to send that way. If you can't, we have in the past gone in and done that coding on our side, and we have scripts to be able to do that. The coding I'm showing on the screen actually comes from the USGS, and we're coding their data on our side. But what it allows for us to do is bring in data from USGS, flood warning systems, the Corps of Engineers, whoever, and put it all in one place, all in one database, all brought in the same way, all with the same kind of time steps, all displayed in one place, and all given equal weight and quality controlled the same way. That way we're not having to go to one place to pull one piece of data and quality control it, and go to another place and pull another piece of data and quality control it. It's all in one spot, it's all displayed together. We can overlay it on our radar and be able to see everything all in one spot. Now let's talk about just a couple of the ways the Weather Service uses the data. This graph is an example of rain gauge data from a flood warning system over about a 6-hour period in 15-minute increments. It actually is reporting in 1-minute increments. I've just graphed it out in 15 minutes. The Weather Service actually receives data, if it's sent through MEDAS, in 5-minute increments and 1-hour increments. And then we can go, if the partner has a website we're allowed to access, we can look at the 1-minute data, the 15-minute data, all of that kind of stuff. But we're primarily receiving it in 5 and 60-minute increments. In this example, you can see that it's raining close to 1 inch in 15 minutes. And the rain gauge that's being shown here is the only one from any network within a several-mile radius, and happens to be right where some of the heaviest rain was falling. So immediately there's the value of this site that we otherwise would not have for any other purpose. It's allowing us to immediately in the Weather Service have an extra gauge that we know is quality, and that we have the data available to us in real time, really in 2 different formats, getting it into that SHEF format so it's in our system, but also being able to come into the partner's website and see it directly so that we can actually get it a little faster that way and see the finer time steps of 1 minute and that kind of thing versus what's being sent to us. Because if it was all sent to us, we'd have this ridiculous amount of data in our hydro databases. So being able to go to the partner's website as a secondary way of viewing data is very helpful to us. We do use radar to estimate rainfall, as shown in the image on the right. This is the graph you just saw was from Elliott City, Maryland in 2016, and was the rain gauge that was there. The circled area on this graphic on the radar is estimated to have received somewhere between 5 and 7 inches of rain. But radar estimates at their best suffer from 2 inherent issues. One is that the radar beam gets higher and higher the further away you go from a radar because the Earth is curved. So if you're 100 miles away from the nearest radar, the radar is likely sampling an area thousands of feet up, maybe tens of thousands of feet up. And it could be above where the heaviest rain is actually falling out of the sky, so it may not be sampling the heavy rain properly. The second thing is, even at its best resolution, you see the squares here in the grid squares. It's a fairly coarse grid, especially the further away you get from the radar. So the precision here is not your friend. In this example, kind of the milky white areas just south of the dot for Ellicott City, that's an estimate of around 7 inches of rain. In reality, you see the gauge total here. The gauge is actually located right at the marker for Ellicott City, and that's closer to 6, and that's actually what was observed. So in this case, the gauge rainfall was a confirmation that the radar was doing pretty well, at least in that one grid square. Ultimately, the highest amounts were higher than what the radar estimated, but a lot of this was really good, and the gauges allowed us to almost instantly determine that the radar estimates were solid and something that we could rely on. That said, you know, these radar estimated amounts of 5, 6, 7 inches are pretty extreme, but so you know, if it's a little bit off compared to the gauge, that difference doesn't make much of a difference because it's so extreme to start with. But let's say you're talking about one of these areas further off to the west, and you get a gauge value that's a half an inch different. That half an inch could make a difference between whether it's going to flood and whether it's not going to flood. So having the gauge data to either back up those estimates or let us know very quickly, because they're real-time gauges, that those estimates are way off is really, really important to us being able to protect life and property and get warnings out to the public in a timely, quick manner. Another way we use rainfall data from flood warning systems is for quality control purposes, or for filling in gaps between other data. On the left here is an image of software that we use in my current office to look at radar estimated rainfall, and then we either include or exclude gauge data. In this example, maybe the precipitation that's shown in southeastern New York didn't really happen. If the gauges there showed 0 precipitation, we could take the gauge data, replace the radar data with that gauge data, and it would take that area to 0 instead of it showing light precipitation. The flood warning system data also might fill in gaps between existing rain gauges, like is shown here on the right. Density and redundancy aren't necessarily a bad thing either, even if it doesn't fill in a gap. If you have 2 gauges, as far as I'm concerned, that are on the same street, half a mile apart, they're not necessarily going to have the same values, and one of them might get clogged up and the other one might be fine. So I don't think there's ever too much data, especially if it's kept in good condition. I want to briefly touch on another way we can fill in gaps, and that's through the CocoRa's network. If you're familiar, the Community Collaborative Rain, Hail, and Snow Network that's started in Colorado and is now all across the country in Canada and other places as well. The way that flood warning systems would work with this data in our process here at the River Forecast Center is that the CocoRa's data is reported on a daily time scale by human observers. So it's high quality data, but it's only once a day. So these other real-time gauges, the flood warning systems, the National Weather Service and FAA automated systems, USGS's rain gauges, other things like that that are real-time with a finer time step, we can then use that data, the higher frequency automated gauges, to help us disaggregate that daily value from CocoRa's into smaller time periods. So let's say that the CocoRa's observer reports half an inch of rain in 24 hours, but the nearby flood warning system gauge only reported that it rained between noon and 6 p.m. Then here at the RFC, we can take that half an inch of rain that was reported by the CocoRa's observer and put it all in the time block between noon and 6 p.m. rather than spread over the entire day. So that's a way that these networks the crowdsourced human networks, the automated networks, they all work together, and we can all use all of them within our operations. Let's talk a little bit now about the back and forth collaboration between flood warning system owners and operators in the Weather Service. Flood warning system operators can help the Weather Service really by just staying in communication with us. Letting us know when a gauge is out of service or malfunctioning lets us take it out of our work processes to where we're not having to consistently take out a 0 on a day it rained or take out a 1-inch value on a day it didn't rain. But more importantly than that, let us know when the gauge is back in service, even if you didn't let us know it was out of service, because if we see it's wrong, we'll take it out ourselves. But letting us know that it's back, it's fixed, and it's good lets us know to turn it back on in our systems so that we can start using that quality data again. Another big thing for us is the more metadata we can get on a site is really crucial. Number one, we want to make sure that we put the gauge in the right place within the network on our maps so that that way it's affecting the right things. It's in the right radar bin. It's able to skew the radar in the right spot, that kind of thing. And if we can see the sighting of the gauge, whether it's a sketch or a photo, that can be helpful to us as well, because that way if we have a question about maybe we feel there was an undercatch in an event, having some idea of the sighting may let us know if there's a reason why there might be an undercatch in an east wind or versus not having an undercatch in a south wind, that kind of thing. And it's also very helpful for us to know if the gauge is heated or not, especially in this part of the country where there are many months where it would just be reporting nothing until the snow melted. All that kind of information really helps us know how to best utilize the data. And then finally, if you're planning to make a maintenance visit to a gauge, it can't hurt to let your local National Weather Service point of contact know beforehand. They might be interested in coming out to look at the site and get some of that metadata information themselves, to where you won't necessarily have to even do it for them. Especially that would apply if your site's a combination rain and stream site. In those situations, I would say most Weather Service offices would like to get out there if at all possible. And by the way, I should mention in COVID times, we are doing field work. It requires being alone and in a car by yourself, but we are doing field work. It is something that's happening. So we can get out and do this kind of stuff, especially since this is an outside environment. We can get out and do sort of a joint field visit in these kind of situations if you're out there. Turning the tables a little bit, we can help flood warning system operators by making the data more visible and giving it added value. The data can be not just displayed within our systems locally for us to use, but as long as everybody's comfortable with it, we can display that data publicly on National Weather Service websites. We can use them and reference them in flood warning decisions regardless, and they can be utilized post-event to help us understand a flood or a heavy rain event before the next heavy rain event or flood happens in the same place. That happened in Elliott City between 2016 and 2018. We did a very thorough review of the data in 2016, not thinking we need to use it again 2 years later, but we had already done that review and knew what sites we had, what type of information we had, and it was all ready to go again when we had to use it again. We're also a guaranteed user of the data. That data will always have value to us as long as the flood warning system is well maintained and we have accurate and proper metadata. So there will never be a point where someone can come to you and say, this is worthless information and isn't worth the money you're spending on it. As long as we're using it, that's not true, because it will be used and it is worth every penny as long as we're putting it to good use. Weather Service can also provide assistance in helping determine locations to put sites if you need it. We may be able to provide an analysis, since we're bringing in data from all these different sources. We may be able to provide an analysis of where all the rain gauges are within our network and help identify places where gaps could be filled. The map on this slide shows one rain gauge flood warning system network we were able to go in and plot all the other networks alongside this one. And this site that's circled here, we recommended to be added because it was in an area where there was absolutely nothing else. We gave another site to them as well, which ended up not being feasible for them, and that happens. But we were able to go in and do the analysis to say, these are the best places that would fill gaps for us, and then they looked to see if they could make them work. Now, as far as siting a rain gauge, what's the best place to site one? Well, the perfect place to site one is protected in all directions, like an opening within a grove of trees, so that you're catching all the rain that's coming down and you're not blocking any of the rain that's coming down. But how often can you actually do that? Really almost never. So let's be more realistic and stick to the basics. The gauge has got to be level. If it's just because it's called a tipping bucket doesn't mean it needs to tip to one side. The gauge should be no closer to an obstruction than twice that obstruction's height. So for example, if you have a 20-foot tall house, the gauge needs to be 40 feet away from it. And if you can have a windshield like the one that's pictured around the gauge, that will help accuracy by reducing the wind turbulence in the vicinity of the gauge. And one last thing I want to touch on is quality versus quantity. I mentioned several slides back that I'm a firm believer that you can never have enough data. Having 2 rain gauges on the same block is not a big deal. It's not a bad thing, as long as they're both good. If someone came to me with a flood warning system with 50 rain gauges, but they're never maintained and the data is routinely proven to be either unreliable or just out to lunch, but someone else came to me with a flood warning system with 1 rain gauge that's routinely maintained and the data is consistent and reliable, I'll take the 1 gauge over the 50 every time, even though I would love 50 rain gauges. The quality matters, because 50 bad rain gauges, we're going to take them all out of our system and not use them. 1 good rain gauge, we're going to rely upon every single day. So that's kind of how we approach things. And I will tell you that rain gauge data from flood warning systems has been a part of my life for more than a decade now. Every single day, every single rain event, always looked at, always used, always valuable, and often vital, because without it, we would not have knowledge that we do have. So that's it for me. There's my contact information. Even though I'm a little less involved with some of the stuff that I used to be, now that I'm in this new position, I'm happy to answer questions now or down the road. Flood warning systems seem to be coming back from what David has told me, so into the area I'm currently in. So I'm looking forward to having those integrated into our operations here at Northeast River Forecast Center again after a bit of a hiatus in some spots. So I'm really excited about that. And with that, put your questions in the question box and we'll get to them as soon as David is finished, and I will turn it over to David to continue the presentation.
Thanks, Jason. Should be switching over to David now. Give him an opportunity to share his screen. That going. Looks like we can see it, David. Go ahead.
Okay. Thank you, Brad and Jason. That was a good presentation, Jason. A lot of good information there. Today's presentation is really, from my standpoint, is more of a back to the basics. Don't think you're going to earn a PhD off of the information provided here from what I've got today, but it's more of a back to basics and just some things that sometimes even us old dogs need to be reminded of as we go through making measurements for precipitation and rainfall. So let's start off with how much, wait a minute here, my slide's not advancing. How much is an inch of rain? You know, we talk about, you know, we got 1 inch of rain, 5 inches of rain, 6 inches of rain, ½ inch of rain. Well, you know, we need to understand how much it is. if you got an inch of rain over 1 acre of land, a little over 200 feet square, that's 27,000 gallons or 3,600 cubic feet of water. If you take that same 1 inch of rain and move it out over a square mile, which contains 640 acres, you're looking at 17.3 million gallons of water just from 1 inch of rain, or 2.3 million cubic feet of water. And cubic feet, commonly used for discharge measurements. So just how much is a cubic foot of water? Well, a cubic foot of water is just under 7.5 gallons, or just over 62 pounds of water from one little simple cubic feet. And if you had 1 cubic feet per second of discharge in a day's time, you'd have 646,000 gallons over the course of the day. So, that little inch of rainfall, if it all ran off or could all be captured, would be rather accumulative in what it goes through. So there are a number of impacting factors when it comes to measuring precipitation. Jason talked about some of those. Intensity is a factor. Some areas where, you get light rains or, maybe 1 or 2 inches an hour, that's one thing. But if you're trying to measure hurricane typical intensities, such as Houston or Eastern North Carolina or Florida, or the areas where you're measuring these high-end rainfall events, that needs to be taken into consideration when you're thinking about or designing your flood warning gauge and your precipitation measurements as to what type of intensities are you going to have to be dealing with. Jason talked about location of that gauge. Just kind of like any other real estate question anybody have is location, location, location. Everybody talks about the importance of being in the right location at the right time. Wind, Jason talked about obstructions and being out in an open area with a grove of trees around you. It's at an adequate distance away, but you do want to protect your gauge from wind. I remember seeing many years ago a study that said in the typical standpipe, what we were all grown up with in the alert world, that for a 10-mile-an-hour wind, crosswind blowing across the gauge, you may lose 10% catch. So, whatever you can do to reduce the wind impacts on your rain catch would be worthwhile. Obstructions goes to just simply that. You don't want trees growing over the top of your rain gauge. The instrumentation that you use. The instrumentation has to match what it is you expect out of the system. When we're talking about intensities or resolution, we'll talk about that and more, significantly more here in just a minute. And then maintenance. That's always close and dear to my heart. Is, as Jason said, if you're going to put the gauges out there and don't maintain them, you're better off not to put them out. So maintenance is key to any flood warning or rainfall monitoring system. And I'm sure others of you could come up with different factors that would have an impact on this flood warning system that you may or may not be putting out. So as an overview of some of the things here this afternoon or this morning, as Brad said, will depend on where you're at. We're going to look at some general requirements for measuring precipitation, the types of instrumentation that is out there on the market. We're going to look at quality assurance and quality control. What are those? Are they the same thing? Are they different? Where do we stand in that? We're going to also look at maintenance issues, some common maintenance issues that we've found over the time. Want to look at some data analysis, post-event analysis, pre-maintenance analysis, and then some case examples, and finally some closing questions we'll get to. General requirements. There's a number of things when the planning of your gauging network, and if you've already got a network, maybe it's time to sit down, if you haven't done this in a while, and reevaluate the requirements of that network. Maybe if it hasn't been done at all, you want us to come up with, what do we expect out of this network? What resolution? Newer technologies are out there from maybe when some of your network was put in. Are you happy with what you got? Do you need to upgrade to different technologies, get better resolution? what kind of accuracy does your network require? Some people will argue, well, flood warning, we don't need the level of accuracy that they do for a climate station or for some other purpose, for agricultural maybe. Does it have to have the same accuracy? Well, I've found over the years that if you will step your accuracy up a little bit, maybe you can get other users wanting to use your data and potentially have additional funding sources to support it. The catch area, the funnel sizes. A lot of us are using 12-inch diameter buckets. Some are using 8-inch buckets. Some are using a 3 or 4-inch diameter catch area. That rain gauge, Jason's slide, remember, you talked about the radar pixels, and they're, I think, like a 1 kilometer. Well, that little 12-inch diameter rain gauge is a very, very small area compared to that radar pixel. So it could be hit and miss. That's why, when you get that verification from a real-time gauge to support the radar estimates is very meaningful. The timeliness of your reporting. Do you need the reports, every tip of the bucket? If you get a report every 5 minutes, is that accurate? What about if it's doing GOES satellite? If you're only getting a report once an hour, is that adequate? A number of things have to be defined as what does your system, what do your users of your data require? What do they want? And then the unit of measure, the imperial measurements or metrics, recording and non-recording gauges, and then whether it's a manual or an automated gauge, a COCO ROS versus a real-time telemetry system. All of those are issues that need to be spelled out somewheres in your requirements documents for your system. You say, well, why do we need that if we've already got a system? Well, how do you know that you're doing what you need to be doing? How do you know that your system is performing as it should be performing and satisfying the needs of your community if you can't define the requirements? Instrumentation for measuring precipitation. I've listed 4 here that are common. There are others, different technologies out there now looking at different ways of measuring precipitation. But these are 4 of probably the more common ones right now: the weighing bucket, tipping bucket, and each has the pros and cons. We'll talk about some of those. Disdrometers, radar, and for radar, I'm not talking about the radars the National Weather Service is using, but rather sensors that mount out at your gauge, and they use a radar beam to look at the rainfall happening around them and measure that. And then the drip counter is a newer technology that's out there that some of the instruments are using. So far, I haven't seen any major problems with those. They seem to be working fairly reliably. So what instrument is best suited for your need? There again, we got to go back to the requirements and define and know what your requirements are to help determine the best instrument for your case. Some people think, well, all we can use is tipping buckets. No, flood warning systems around the country are using different instruments, not just tipping buckets. Sorry about that. So a couple years ago, I set up a test bed, and this is not to help you make a decision on which one you want. This is to help you understand the importance of knowing what you're getting. We set up a test bed of 6 different precipitation measuring devices. One was a drip counter. 2 of them were disdrometers. There were different models made by the same manufacturer. One was a radar sensor, and then we had 2 tipping buckets, 1/100th of an inch with an 8-inch catch funnel, and a 1 millimeter tipping bucket with a 12-inch catch funnel. The manufacturer stated accuracy for each of these devices. The drip counter was plus or minus 5% at a 1.97 inch per hour rate. Accuracy is really, really, really dependent on the rate of the rainfall. So that's something you need to consider when you're looking at this. The 2 disdrometers, both stated accuracy was less than 5% error. And then in parentheses, they said weather dependent. Never been able to understand or get them to answer what that really meant. The radar unit said it was less than 10% error up to 7.8 inches per hour. The 100th of an inch tipping bucket had no stated accuracy, but said it was good up to 25 inches per hour. And then the 12-inch bucket was a plus or minus 1.5% at 3.6 inches per hour. So all of these different accuracies at these different rainfall rates, you can see it kind of becomes a mixed can of worms when you try to compare them. But that's what we did over a course of a little over 2 months. We had all 6 of those gauges within a 10-foot circle, 10-foot diameter circle, measuring rainfall. And during that 2-month interval, or a little over 2 months, we had 12 or more rain events ranging anywhere from 0 to 4.5 inches per hour intensities. And you can see on the far right-hand side of this graph that one of the distrometers, the green line there, barely reported over just under 10 inches, a little over 9 inches of rain. And the radar unit, the dark blue one at the top, reported over 14 inches of rain. So just in 2 months, we had a 33% discrepancy or deviation in the amount of rainfall that was measured between these 6 devices. The orange dots there are showing the intensities of the rainfall from each of those rain events. The highest intensity that we had during that 2-month interval was 4.5 inches per hour. If we go back and look at a single event out of that 70 days, this one event here lasted about 45 minutes. It was just under an inch of rainfall, average based on all the sensors. But notice the flip-flop on the right-hand side. Let me back up one slide. The dark blue line up there near the 14 inches, that was the radar unit over the period of 2 months. Come to this one single event, now that same unit is the low reporter. And we had another flip-flop of one of the distrometers. So things can change in accuracy, as I said earlier, based on the intensity of the rainfall that's happening. There can be other factors that change that accuracy, but that's one of the biggies if everything else was alike. And you see that, here we see in, plus or minus 20% deviations or errors, and all of which is outside the range, the stated range of accuracy from the manufacturer. So in addition to instrumentation, the next biggie is your QA/QC plan. What is a QA/QC plan? Do you have one? Well, borrowed from the ISO 9000 standards, they show this little graph here of a quality system. Within that quality system is a subset of a quality assurance plan, and then a smaller subset of quality control. So what are you doing? In order to have a quality system, you have to have the other 2 elements there contained therein. Quality assurance are those processes that focus on what's going to be done to assure that the quality requested is being achieved. In other words, if you want high quality data, then what are you going to have to do to maintain that? What are you going to have to do to obtain that? A QA plan is set to prevent problems, or the goal there is to prevent those problems. It's a proactive stance. So you take those necessary steps ahead of time to ensure quality assurance. You have defined standards and methodologies. How do you go about calibrating your rain gauge? How often do you calibrate the rain gauge? How often do you perform maintenance visits? All of those are standards and methodologies that should be defined in your QA plan. And it's going to require the full team's involvement, from managers all the way down to technicians. Everybody has to have input. Everybody has to have quote unquote ownership in this QA plan. The QA plan is going to come before quality control, because the QA plan is going to spell out what quality control is going to be done, when it's done. Quality control is that procedure that focuses on fulfilling the quality that's been requested. Here you're going out to identify and fix defects, hopefully in a preventative manner, but making sure the funnels are cleared, making sure the vegetation hasn't grown over the gauge, making sure the battery is adequate to keep it going when the clouds are there and there's no charging. It's more of a reactive response rather than the proactive that we talked about under the assurance plan. And you're going to confirm that whatever methodologies and standards that were already defined, this is what you're going to follow when you're out in the field doing the work. And your testing team has to be committed to the task. You can't just be doing it nonchalantly. Maintenance is going to have to begin when you start looking at the data before you ever go to the field. If you're going out in the field doing maintenance and you've not done any maintenance reviews, then you're starting already with a handicap. When you look at a graph and you look at a 2 or 3 day interval and you see consistent one tip of the bucket, 3 hours later, one tip of the bucket, 3 hours later, one tip. It didn't rain that evenly across a 2 day period. You can look at that graph and see that, there's a clogged funnel before you get there. You know that that's going to be problem number one. Maybe not the only problem, but problem number one. Before you go out and look, this site, in the fall of the year, the battery keeps dying. Well, you go back and look for the last 3 years. Well, every fall the battery dies. It's not like somebody stole the solar panel. What's going on with that? Is the solar panel aimed in the wrong direction? There's a number of things that, could create this problem, but knowing ahead of time before you get there allows you to go out there with at least a thought as to what you might find when you get there. And then looking similar as we did in that test bed, but looking at accumulated rainfall for a given area, a basin or whatever, look at disparities in the reported data from a collection of gauges, kind of what Jason was talking about earlier with, when they compare different networks, gauges from different networks, and use it as a means of quality control, their data. Well, you can do this before you go out in the field on your maintenance visits to see what is happening or has been happening in your network. If we take a closer look at that last little graph, we can see that way back over on the far left-hand side here, the green line had already flattened out. And then it gets about the middle, it gets even worse, a little arching in there. So, there's a clogged funnel that's leaking through, but it actually started way back when on the far left-hand side. We see the same thing on the right-hand side. There about the middle of the light blue line. It, starts just a gradual climb rather than steeper inclines like the rest of the measurements are. There's just a number of different things. I could look at that graph right there and see at least 6 or 7 indicators of a problem at a rain gauge before you ever get there. You need to go to these sites already with an understanding of what might be wrong there. And this is the purpose of these data analysis. Well, everybody has their own definition of data maintenance. We went in and did a site survey and inspection on a network several years ago, and the technician had told us that they had been to all the sites within the last month. And that's what we found on the first site we went to. And what you're seeing is the top of the standpipe there at the top of the kudzu. The antenna mast pipe is already broken off. And if you look real close in the kudzu there, you'll see the top section, the funnel and the tipping bucket inverted. The little silver band near the bottom of the circle is the top of the funnel. Actually, the kudzu vines had gotten on it. It took too much time, they said, to put the screws back in it to hold it in place. So they just set it on there loosely. And so the kudzu had pulled it off, broke it off, had it upside down. But somebody was just there just a month ago, they said. I don't believe that. Maybe they may have been there, but the gauge, they certainly didn't work on the gauge when they were there. This one was, again, after another presupposed visit. The grapevine is growing pretty wildly there, but it doesn't take much to clog up that funnel and keep it from reporting correctly or accurately. You have to actually get out and do something and not just drive by with a windshield. So where is the prevention that's going on here? How is it we can expect quality data when we see these types of scenarios? Quality maintenance also requires resources, hopefully more than a rock and some flat washers to prop your bucket up to get it level. The springs have rusted out in this one. Unfortunately, out of a 14 gauge network, when we went in to do inspection on this one, we found 3 of them that had rocks, and or one of them had taken a handful of rocks and duct tape and made it into a bigger ball to hold the rocks all together and propped up a bucket. Notice the back leg back there on it's already way down low. So there's no way this tipping bucket is going to report accurately. But resources is more than just materials. The rusty springs could have been replaced for just a few dollars. But if you don't have those in your spare toolkit, how many trips do you have to make out there to get that finally done? Resources also involves personnel training, just as those that are here today, watching the webinar and listening in. How do we stay up to date? What's the latest and greatest technology that's out there, the greatest and latest techniques that we could apply to our work field? All of those resources, it's more than just money, but we got to have training to know what to do, how to do it better. There's always room for improvement when we go through this. Maintenance also, when you're doing rain gauges, requires verification, a tipping bucket calibration record. This graph here is actually over a 2-year period. The leftmost 4 vertical bars are showing the 4 calibrations were done at different rainfall intensities year 1. A year later, there were 5 actual calibrations done on this one bucket. And we do more than one occasionally just to show consistency. In other words, are they just one and done? That's fine. But occasionally we throw one here and we'll run it 2 or 3 times to make sure that it's consistent. Because we have found that it tests good once and the next time it's way off and you can't figure out why. So are you documenting? Are you putting out the effort to be able to prove this later on when you're showing the quality of your data? And again, notice the difference in how it calibrated the percentage of error versus the rate of rainfall that was applied to it, whether it was, a 3.5 inch per hour or 1.5 inch per hour rainfall rate. But at least it's consistent between the 2-year test periods. And then I always think the number 1 requirement for any maintenance is that we need to be looking for the unexpected. This is one of those where it tested good, but we ran it through a second time, it tested terrible. Run it a third time, it tested good. Trying to figure out what was going on. So you sat here, we finally saw what was happening, and you see the bottom of the funnel, the inner funnel here, just before the water comes to go into the tipping bucket. So we start the calibration technique, and the water starts dripping down into that funnel, runs along there, and just all of a sudden, like you blink of an eye, look what's happening to the water. It's not going in the bucket that's measuring the water, it's hitting on the other side. And the bucket tips and comes back again, and all of a sudden the water's back to its correct side again. No, it's like, why? What is going on? Well, we tore the bucket apart because you can't really see up inside it, and we look in it, and there's a groove in there, and there's actually debris and stuff in the bottom of that funnel, and it was wicking across and started causing the water to run sideways. So one of the fixes we've applied in this particular scenario was, you see the top right there where the funnel has the little V-notch groove down in it, is we actually took and ground off that outer lip so that the water can't bridge across from the 2 lowest points on the bottom side of that funnel. Or if you get spider webs or dust up in that V-notch, it fills up and allows the water to wick across as a means to get rid of it or to prevent that wicking from happening. And then maintenance requires documentation. You've heard it said, over and over and over, no job's finished till the paperwork is done. Well, you need to be documenting all of your maintenance activities for rain gauges, showing the tip and bucket calibrations. If you've got water level sensors, showing when those calibration values there, solar charging for your battery. This is just maybe a third of a calibration document maintenance sheet that is there. So the question then becomes, do you have a healthy system? Well, one of the joys of out working rain gauges is, we get to see herds of deer and flocks of turkey and, different things running around. And hopefully, thankfully, they're all, good and healthy. They enjoy running around. But occasionally we run across something that needs life support. And sometimes it's beyond life support. So is your system healthy? Or is it in need of something we've talked about here today? And with that, I will close and turn it back over to Brad for any questions he may have accumulated.
Thanks, David. It's pretty interesting, and we have had a few questions. So I'm just going to start top here. This first question is for Jason, and it's how does MATIS and Chef compare to Alert and Alert 2 systems?
So hopefully in a perfect world, output from Alert and Alert 2 turns into output in MATIS and Chef. In most cases, actually, it does. It's sort of I don't want to call it a magical process, but the Alert and the Alert 2 data can be fed from vendors into MATIS, and then MATIS turns it into Chef for us. So that's really actually the best and easiest workflow, is for an Alert 2 network to, through a vendor, get the information into MATIS, and then let MATIS do the work of getting it to us, because that way there's no need for anybody to figure out how to Chef encode data. It also can be Chef encoded before it's sent to MATIS. It'll work that way too. So either of those methods, but hopefully all of those 4 pieces of the puzzle, or 3 pieces of the puzzle, are going to work together in concert to make it all work out. The systems that we used in the DC area largely are all working that way.
I guess the next question kind of adds to that. If more and more observations and networks are added, how is the data quality checked before being used for warnings and operations?
So the way we're doing it here at the RFC is, you sort of saw on that one slide, the little dot plot. We have different things we can do with that dot plot. So for example, on a day like today where it's raining, we can have the dot plot be gauges that report 0 versus gauges that are reporting a value. And then that way we can isolate all of the gauges that didn't report rain on a rainy day, and we know those are the bad ones. We can do vice versa on a dry day and isolate out the ones that are reporting something when there shouldn't be anything. Where it gets a little trickier is if you have, let's say, 2 gauges that are a couple miles apart, and one's reporting 1/10 of an inch, one's reporting 3/10 of an inch. Is that difference real? Is it not real? Last week up here, we had one small area in, I believe it was New Hampshire, that had a thunderstorm and ended up with a fairly significant rainfall in just one tiny area, and it happened to hit a gauge. So, the first thing what we thought was, this one site has a significant rainfall and there's nothing else around it that does. Is it real or is it a malfunction? And that's when we bring it up against the radar and see, does the radar have anything in that spot? And sometimes it's a judgment call whether that value is real or not. In this case, it sort of matched up with the radar enough that we kept it. But that's really when it's the hardest for us to QC, is if we have spotty summertime or what we call convective thunderstorm rainfall, where it isn't going to be uniform across an area, and it could vary, frankly, between those two gauges 1 mile apart, depending on where the storm is. That's where we really have to put a lot of effort into the QC process. And I will readily admit there can for sure be times where we throw out something good because we didn't realize that it was because it's so spotty. Or we may ultimately, that example I gave with the 1/10 of an inch and the 3/10 of an inch, we might end up throwing both of them out if it appears that we can't really determine if either of them are valid or not, or we might keep them both if we can't determine that one should be thrown out over the other.
Okay. Next question is, can the National Weather Service also help for best location to site a flood warning system? You mentioned that you would help with rain gauge placement, I think. Maybe they're looking for some additional help.
I think, and obviously I'm in one office, I can't speak for everyone in the Weather Service in that way, but I'm pretty confident that most of my former service hydrologist colleagues would be more than happy to talk with any locality about where any type of gauge would be best placed for operations. The locality often knows where their problems are, but the Weather Service knows hopefully knows both where those problems are and where we may be having problems seeing those problems. For example, if there's an area that we know is a frequent flooder, then maybe it's best to have those sensors, whether they be rain, stream, or otherwise, upstream of that point rather than directly over that point, so that you have the ability to see what's coming rather than see it once it's already there. So that's the kind of thing that the Weather Service can definitely help with, and looking into, is that site upstream going to really show you what you want to see, or is there going to be some other small stream that comes in between that point and your interest point that will make putting that gauge upstream an invalid placement? So definitely I think that's something that Weather Service offices can assist with.
Okay, the next question. Does the National Weather Service typically estimate the uncertainty associated with rainfall interpolations?
I think the short answer to that question is not directly. When we take the radar estimates, and we take the radar estimates and the gauge values, and they ultimately get combined together into a single multi-sensor system that becomes our best estimate precipitation. And then, the way we display that out to most other people is in ranges of values. So in that way, there's sort of a non-measured uncertainty because no one's seeing a specific value. They're seeing that it was between 1/4 and 1/2 or between 1/2 and 3/4. They're not seeing that the value at this grid point was 0.62, So that, from a scientific perspective, there's not like a range of possibilities associated with the best estimate precipitation. It's simply a gridded value over an entire domain that's utilized as the best estimate in the end.
Okay. Next question is, does the National Weather Service have any interest in other data or information such as soil moisture, hail, real-time discharge, etc.?
That will be the easiest one for me to answer. Please, 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 yes. And that's all I have to say to that one.
Perfect. That's kind of what I thought you were going to say. Switching over to David here. This question's for David. It says, can you share any examples of providers that have obtained additional funding by investing in more accurate sensing?
The case and example would be, yes. I mean, I know some people that it wasn't just the accuracy, but it was the quality of maintenance they were doing. You know, they got other people that were interested in the network, and so some outside sources ended up buying additional gauges that allowed them to add to their density. It wasn't direct funding, but indirectly there were some additional benefits provided to the flood warning network. Because they saw the value and what was out there, and they thought, well, we need some more over here in this other area. So private enterprise, public utilities, different organizations on more than one occasion have actually come up and footed the bill to add some additional gauges.
Okay. We've got 4 more questions, looks like maybe 5. Hopefully y'all have time to hang on. But the next one's pretty quick. How long should a battery backup last? 24 hours, a week, a month? Any thoughts on that?
Well, it depends on your requirements for the system. I mean, I've got sites that have run for, months on just a battery without solar charging. Other sites are designed to run for max of 2 weeks. Some typical, you'll see 30 to 40 days. You ought to plan your system around that, I think, as a good rule of thumb, just so that, because if it quits charging, you might not be able to get out there the next day or maybe even the next week, but hopefully within, a couple of weeks, you can get out there and fix the problem. So it really is a system requirements question more so than how long should it last.
Okay. This next question has to do with gauges being affected by wind. I'd ask, can you talk a little more about wind impacts on rainfall measurements and what instrument or installation you would suggest to be best suited for the kind of environment? And they give an example of a certain gauge they have reporting something like 21 inches of rain on a day when they have really high wind.
Well, the question is that rainfall value they think high or low? And I've seen both. I've seen wind-induced rain. The wind actually caused the gauge to over-report. In other cases, the wind, caused it to under-report. So, as Jason said, a windshield around a gauge is of value. Properly locating it, away from tall obstructions, but within a quote sheltered area to where some of the higher winds are diverted away from the gauge. Here again, you're measuring wind, on a normal day, or you measuring 140 mile an hour hurricane winds. It's unfortunately there's not a direct answer, I don't think, for all that's going to cover all situations.
It was a good answer nonetheless. Next question, is it an oversimplification to say that all rainfall measurements are estimates?
And I would turn around and ask, is the sky as blue at your house as it is at my house? An estimate, yes, because you're only looking at a 8-inch diameter or a 12-inch diameter area over, how many miles and miles between your gauges. That's what it did at that particular case. I think it is possible to get high quality, high resolution rainfall measurements at a point in place on the ground. But how that point transfers 100 feet away is unknown.
Okay, and this will be our last question, and we'll have to sign off. It says, our process utilizes MRMS data, which is radar corrected by greater than 20,000 gauges checked by METs. To alert for potential flooding, we compare with NOAA Atlas 14. However, this has been down due to a flood at the NWS computer facility. How concerned is anyone about the recent frequency of data outages and computer infrastructure problems?
Sounds like a question you need to answer, Brad.
I'm concerned about my own network connectivity here at the house. So right now, Jason, do you have
I'm
something
not
to
sure
add
how
to
to
that?
respond.
I can definitely say that there have been challenges with that, the results of that flood. We've been experiencing them here too. There are things that we've not been able to receive here as well. I do know that they are working both on trying to triage the situation after the incident there, but they're also trying to develop and fast track as much as possible a longer term solution that will work so that something like this can't happen again. I know both of those things are sort of ongoing at the same time, and hopefully we'll see things heal up sooner rather than later.
All right. Well, thanks, guys, for the presentation today and for answering the questions from folks. For those of you that are still on the line, I will get a certificate out. These webinars are good for 1 hour of credit towards your Certified Floodplain Manager certification with ASFPM. That'll take me a little bit of time. I got to have my graphic designer put the thing together. And then, yes, this meeting was recorded, and a link to the YouTube video on our YouTube channel will go out here in the coming days. So I'll look for an invite to the next webinar for the month of April. I think these are on the last Wednesday of every month. Again, I appreciate your time, and y'all have a great day.